Hello everyone, welcome back again to the course Comprehensive Slope Stability Analysis using Plaxis 2D. This is tutorial number 8, Slope Stability Analysis using Mohr-Coulomb constitutive model. So we will model the slope geometry in this lecture, and as you can see, we have this geometry and the slope is one horizontal to one vertical, and we will model the geometry of this slope using boreholes in Plaxis 2D, and we will use a Mohr-Coulomb model for defining the material of the soil. So also we will estimate the factor of safety using Plaxis 2D, which is based on a strength reduction method, which we explained in some previous lecture. Also, we will identify the potential failure surface in Plaxis 2D. So let me open the Plaxis software first, and we will copy the title of this lecture, and we will click on start a new project, and in here we paste the title of the lesson, which is tutorial number 8. And after that we click on the model. In here, this is a plane strain, and we use a 15 noded element, which is better than a 6 noded element, and we keep the unit as a default, but in here we have to do some changes in contours. For example, we can see the length of this slope geometry is about 45 meter. So in here, in x minimum we set to 0, in y max we set to 45 meters, and we assume this point is the original x y coordinate. So the maximum y will be 20 meter if this one is 0, y minimum, and y max will be 20 meters. As you can see, the maximum height of the slope is 20 meter. So we can, if it is required, we can change this next also. It's not very important if you do some, if you set something wrong in here. So we click OK. Okay, so right now we will start modeling the geometry of the slope. We click on the borehole, and we click on this original point. So for this slope geometry, I will need one borehole in here and one borehole in the tree of the slope, and another borehole at crest of the slope to generate this geometry of the slope. So I will add one soil layer. We assume the bottom is 0 and top is 10 meter. As we can see, this one will be top of the borehole, and this point is bottom of the borehole, so it will be 0 to 10 at the top. And in this lecture, that we assume the water table, this blue line is a water table which is located 3 meter below this ground level. So in here we say the water table is at 7 meter. So we click OK, and we will add another borehole at x equal 15 meter. So again we click on the borehole, and this one is 15 meter. Again the top will be 10 and bottom will be 0, and the water table location of the water table is 7 meter. Then we will add another borehole at crest of the slope. So this one is 15 meter, and the height of the slope is 10 meter. Slope is 1 to 1. So 15 meters plus 10 meter will be 25 meters in x direction. So this one is 25 meter, but in here at top we will set as 20 meter, and bottom will be 0, and the location of the water table also we set as 7 meter. So this one will be unchanged. So we click OK. So we created the geometry of our slope, and right now we will need to define the material properties for this soil. So as I mentioned in the first lecture, Introduction to the Course, the Plaxis software which we are using is Plaxis 2D version. It is version 2024.2.0. So we will use this Plaxis 2D version along this course. And before we start defining the material, let us talk about the fixities and deformation boundary condition. So actually in Plaxis 2D, the fixities and deformation boundary conditions are applied automatically. So it is like this one. For example, the bottom boundary condition is fixed. It means the displacement or deformation of y and x equal 0. And vertical boundary condition at left and right is like this one. It is allowed to move or deform in vertical direction, but it is fixed in x direction. Click on calculate, and it says no node or stress point were selected. I will say it's okay, ignore and calculate. So I will wait until the analysis is finished. And so as we can see, the calculation is being finished, and we are at the last phase, which is a safety analysis. And as you can see, the safety factor is more than 1.5 in here, and it's being constant. So we will wait until the calculation is being finished. So the calculation is finished and we don't have any error or warning. So the first thing, we can check the safety factor. So we click on the last phase and click on edit the phase. So in here we can see sigma m sub sf, which means a rigid safety factor. So it is 1.556. So it means the factor of safety is 1.5 or something more, 1.556. So the safety factor is okay for this slope. And also we can check the failure surface. So we click on the last phase, and in here we click on view calculation results. And so as you can see, we can see this is a deformed shape of the slope at failure. And don't worry about the maximum value, which is 68.58 meter. This doesn't have any physical meaning at safety analysis. So if you want to check the deformation or failure surface, we click on total displacement. So you can see this is the most critical failure surface for this slope. Also we can click on a surcharge load construction phase. We can see the maximum the maximum deformation of the slope caused by this surface load or surcharge load, we can see the maximum deformation is equal 3.427, which is about 3.5 millimeter, and the displacement or deformation is okay for this slope, which is minor. Also, we can check the initial phase. This is a displacement or deformation of the slope based on their gravity loading, which is 0.06, which is about 6 centimeter. Also, we can check the stresses as well. In the slope, we can see the maximum and minimum stresses in y direction. Okay, so we can also check the effective stress. Maybe there's some changes because we have a water table at this location. So for Cartesian also, we have Cartesian total stress, and also we have Cartesian effective stress. As you can see, there's a small change between them. Also, we can check the principal effective stresses, sigma 1, sigma 2, and sigma 3, etc., or principal total stresses, not effective. Also, we can check the pore water pressure. For example, we select pore pressure, and we have excess pore water pressure, active pore water pressure, or total pore water pressure. If I click the pore water pressure, we can see the pore water pressure is only available below the groundwater table. In here it is 0 because there is no water. So this was for this lecture. I hope it was clear. Thank you for watching. See you in the next tutorial.